Hey everyone, welcome back. Hope you're all doing well. In this video, we're going to learn about the window analysis method for delay analysis. The contemporaneous period method is often known as window analysis method. It is a retrospective scheduling method that uses contemporaneous schedule updates to identify and measure how delays impact the as-built critical path. In a Windows analysis, we begin with the approved as planned or baseline schedule. This is our starting point. From there, we divide the project into manageable analysis windows, typically by month or every 2 weeks, depending on the level of detail we need. For each window, we update the schedule with actual progress and any delay events that occurred during that time. Then, we compare this updated window to the previous period to assess how those changes impacted the critical path or overall project timeline. This process is repeated for each subsequent window until the end of the project. Essentially, we're building a timeline of how the schedule evolved step by step using real data from the field. Let's go through this example to see how this method works. Here we've got an as-planned schedule for a project that includes building a main house and a garage. According to the baseline, the entire project was expected to be completed in 112 calendar days or 16 weeks. The schedule for this project was updated periodically, every 4 weeks. In other words, at the end of each 4-week period, we had a new updated version of the as-planned schedule reflecting actual progress and any changes that occurred. To track the changes and the impact of events on the updated schedules, we're creating a table. The first column shows the update number starting from 0, which represents the point before any updates were made. Next, we have the updated project completion date after each schedule update. The following column captures the total delay or impact caused by events during that period. Then we break that delay down into 3 categories: non-excusable, excusable but non-compensable, and excusable compensable. And finally, the last column includes notes on the actual events that occurred during each period. Now let's take a look at the first window. During this period, there was an owner-caused delay to the excavation work for the main house. As a result, the project is now projected to finish in 133 days. We'll update this information in our table. Comparing this to the original plan of 112 days, we see a 21-day delay. Now the question is this delay excusable? Since it was caused by the owner, yes, the entire delay is both excusable and compensable. That means there's 0 non-excusable delay and 0 excusable non-compensable delay for this window. In the second window, nothing happened. No events, no delays, no changes. So the project timeline stayed exactly the same as before. Now, in the third window, things got more interesting. There were concurrent delays. First, the subcontractor walked off the job, which forced the contractor to find a replacement. This caused a 21-day delay to the main house construction. At the same time, the owner made a design change, which added another 14-day delay to the same activity. As a result, the project is now expected to finish in 154 days. Comparing that to the previous completion of 133 days, we get an additional 21-day delay for this period. Now, let's figure out how much of that is excusable. Looking closely at the overlapping delays, the 14-day owner delay completely overlaps with the contractor delay. In this case, since both parties caused delays during the same period, the contractor can claim time extension for those 14 days, but not compensation, because the delay would have happened regardless of the owner's action. Now, what about the remaining 7 days of the contractor delay that didn't overlap with anything? That part is non-excusable. The contractor is fully responsible for it. So to summarize this period, we've got 7 days of non-excusable delay, 14 days of excusable but non-compensable delay, and 0 compensable delay. Moving to the fourth window, there was a 7-day delay to the garage door due to the contractor's fault. However, the project is still projected to finish in 154 days, same as the previous update. This means the delay wasn't on the critical path and didn't impact the overall project duration. So, for this window, there's no additional delay to the project completion. In window 5, the owner made a revision to the garage doors, causing a 28-day delay to that activity. After updating the schedule, the new project duration became 161 days. When we add this to our table and compare it to the previous update, we see that the project was pushed by 7 days during this window. Now, here's something interesting. Even though the owner's delay was 28 days, the project only got delayed by 7 days. Why? This is because before this update, as we saw in window 4, the garage door activity wasn't on the critical path. It had some float. The owner's delay first consumed all of that float. Only the remaining portion of the delay, after the float was used up, actually impacted the critical path and extended the project by 7 days. This 7-day project delay was only caused by the owner. Therefore, it is excusable and compensable. Alright, the project still didn't reach completion in this window, so we move on to the final update, window 6. In this period, there were no changes recorded, so the project completion remained the same and no additional delay was added. Now, let's add up the total delay after all 6 windows, which comes out to 49 days. Out of that total, 7 days are non-excusable delays, all coming from window 3. We also have 14 days of excusable but non-compensable delay, again from window 3 due to concurrent delays. Finally, we have 28 days of excusable and compensable delay, 21 days from the site condition in window 1, and 7 days from the garage door revision in window 5. All right, through this analysis, we've identified a total project delay of 49 days. Of that, 7 days are non-excusable and subject to potential liquidated damages. The remaining 42 days are excusable and eligible for time extension, but only 28 days of those are compensable. Now, we've learned 3 key delay analysis methods: impacted as planned, collapsed as built, and window analysis. Let's compare them across different aspects. Starting with the baseline, IAP relies on the original as planned schedule, KAB works backward from the AS built schedule, and window analysis uses both the baseline and a series of periodic updates. Each method has its own unique approach. IAP inserts delays into the planned schedule to forecast potential impacts. CAB removes delays from the as-built schedule to simulate what would have happened without those delays. And window analysis tracks delays as they occur across defined time windows. In terms of purpose, IAP is useful for forecasting time extensions early in the project. KAB is often used to demonstrate the causes of delay, and window analysis is ideal for understanding how delays evolved over time. When it comes to incorporating actual progress data, IAP does not use it, while both CAB and window analysis do. The critical path assumptions also vary. IAP relies on the original planned path. KAB analyzes the actual path followed during construction, and window analysis captures the changing critical path throughout the project. As for preferred application, IAP is typically used in early stage delay evaluations or claim forecasting. KAB is valuable for claim defense or entitlement assessments, and window analysis is especially effective for complex projects that undergo dynamic changes. Finally, each method has its limitations. IAP overlooks actual progress and resequencing. KAB is sensitive to assumptions about delay logic and order, and window analysis requires consistent and accurate schedule updates to be reliable. In summary, no single method is perfect for all situations. And the best choice depends on the nature of the project, the availability of schedule data, and the goals of the analysis. This concludes our video. Thanks for watching, and we'll see you in the next one.